Hi, welcome to our 2271 tutorial 7 discussion. In our first question, we're going to look back at the use of mutex. This code that you see here is basically similar to what you saw for tutorial 6 question 3, okay, except that in that question we made use of semaphores. Okay, here we are going to transition all of that to make use of mutex. Okay, so for this line over here, mutex new previously was os sem new. Okay, and what we did was we created a new semaphore with a max count of 1 and initial count of 0, and this mutex acquire was actually os sem acquire. Okay, and over here when we press the push button, instead of mutex release, previously it was os sem release. Okay, so of course you can look back at the previous tutorial to just have a quick comparison. Now, what would be the expected behavior of the code right now, okay, with transitioning everything from semaphore to mutex? Okay, let's look at it step by step. In the main, basically we are creating a new mutex over here right now. So once you create a new mutex, the mutex is available. Okay, and for the threads, I create LED red first, followed by LED green. So definitely once I start the OS, this LED red thread will run first, correct? And once it runs, what will it do? It will call os mutex acquire. And since the mutex has already been created, when I call acquire, I will be able to get it. Okay, so this will go through successfully, and I'll be able to control the LED, okay, to switch on the red LED. Of course, once that happens, okay, and I call OS delay, I will basically have a context switch over to the LED green thread. When I go over to the LED green thread, what will happen is I try to acquire the mutex. Okay, but what is the situation now? The LED red thread has acquired the mutex and it has not released it yet, correct? So when LED green thread tries to acquire the mutex, it will not be able to get the mutex. Okay, so it will go to a block state. Okay, and once it goes to the block state, of course, we will transition depending on what LED thread is currently doing. Okay, so of course, if it was in the OS delay, once the OS delay has been completed, it will come back, it will off the LED, and again, it will go through OS delay. Okay, of course, since LED green thread is already in the block state, okay, waiting for the mutex, we will not transition here. Okay, so when I call this OS delay the second time, I will actually be blocking LED red thread, and LED green thread is already blocked, correct? But eventually, after I come to the end here, the closing braces, I'll go back here to another iteration of the loop. And what happens in the second iteration of the loop, I call os mutex acquire again. Okay, so at this point, what happens is again I try to acquire the mutex, okay, but I have not released the mutex from my previous acquire. So because of that, when I try to acquire one more time, it will say that the mutex is not available. So it will go and transition this thread to a block state. Okay, so this is already blocked, correct? And then in the second iteration of the LED red thread, when I try to call the os mutex acquire one more time, it will realize that nobody has released the mutex, so it will go to a block state. Okay, and what will happen is eventually both the LED red thread and LED green thread both will be permanently blocked because nobody has released the mutex, correct? Of course, this is where the push button interrupt handler comes in. Okay, so similar to our tutorial 6, we have configured the switch, okay, that whenever I press the switch, I will come to this port D IRQ handler. Now, what do I do here? In port D IRQ handler, I actually call os mutex release. Okay, so if you recall in tutorial 6, okay, we called os semaphore release, and that basically allowed the semaphore to be incremented, so whichever thread was waiting for it could acquire the mutex, could acquire the semaphore. Now, do you expect a similar behavior over here? Okay, and interestingly, what you see is pressing the button does not change anything. Okay, the LEDs remain off. Okay, so it doesn't seem to behave in a similar fashion to how the semaphore was behaving, correct? Okay. Why is that so? Okay, so this is of course the explanation of what I mentioned just now. Okay, so you can read through that. Now let's go into understanding why the push button doesn't actually work over here. Because if you look at OS Mutex release and documentation, you will see that it states here that the function cannot be called from the interrupt service routine. Okay, so if you had actually or if the code had actually tried to capture the return value, the status, it would have actually gotten an error, okay, which is OS error ISR, which basically tells us that the OS mutex release function cannot be called from an interrupt service routine. So it is important to actually go through some of this documentation to have a good understanding of what is allowed and what is not allowed, okay, in the OS context. Okay, so in this situation, even though you can successfully compile the code, okay, you can download it, when you try to run it, okay, it will not actually work. Okay, so these are some of the things that you must be aware of. The compiler is not able to detect some of these things. Okay, so even though the documentation says that this is not allowed, okay, when you compile, it does not sort of flag off as an error. So you need to know what is allowed, what is not allowed. And of course, a good practice is to actually capture this return codes whenever you have a OS kernel call, so that you know whether that kernel call actually went through successfully or actually returned a error. Okay, so that is a good practice to actually implement in your code. Now let's look at the other return values that you can possibly get. Okay, so what is given here? Of course, OS OK is the one we always want, because that means that the mutex has been correctly released. Okay, but how about OS error resource? That means you have acquired the mutex in one thread, but another thread is attempting to release it. So this is also not allowed. In semaphore, we allow it, correct? One can take the semaphore, another thread can release the semaphore. But in mutex, this is not allowed. So if thread A has acquired the mutex, thread A must release the mutex. Okay, and the reason why it is that the rule is in place is because the whole idea of mutex is you want to protect a critical section of the code, okay, while a particular task is running. Okay, so if this particular task is accessing a shared resource, some critical section of the code, it is our responsibility to ensure we lock it, acquire the mutex, and after I finish, I release the mutex. Okay, so that is why it has to be within the same thread itself. Okay, you cannot have one thread locking it and another thread releasing it. Okay, it will return as a OS error resource. The other error situation is OS error parameter, where you attempt to use a mutex that has been deleted. Okay, so under mutex, you can create a mutex. You can also delete the mutex. So it could be a situation where one task created a mutex, and after using it, it accidentally or without realizing it deleted the mutex, and another task actually went on to try and use this mutex. Okay, then it will actually have a error message again. Okay, and the OS error ISR is basically what we saw just now. Okay, so from this example, what is clear is it's always a very good practice to capture the return value whenever you have a OS kernel call, so you know whether things are happening the way you expect them to happen. Okay, so that is a good practice to follow. Question 2 is on thread flags. Okay, so if you look back at our lecture slides, okay, you can see that each thread actually comes with a built-in flag mechanism. Basically, you have flags from 0 all the way to 30. Okay, total of 31 flags. Okay, and in order to use the flags, what is important is when you create the threads, you must capture the thread ID. Okay, so that is the important thing. Okay, which you can actually see in our sample in our examples in our lecture slides. Okay, in this question we have 3 threads. Okay, the LED red thread, green thread, and blue thread, given highest, medium, and lowest priority. Okay, so what is going to happen is, okay, what is expected is at time t equals to 0 plus, okay, the green LED will be on for 1 second. At time t equals to 1 plus, the green LED and the blue LED will both be on together. Okay, on together for another 1 second. Okay, at time t equals to 2 plus, both the green LED and the blue LED will go off, and only the red LED will be on for another 1 second. And this process will keep on repeating itself indefinitely. Okay, so this is the expected behavior of the code that you're supposed to write. So how do you go about doing this? Okay, so let's look at this. So the another requirement is you must only use thread flags, okay, and implement the code. And the thread IDs have already been given to you: red LED ID, green LED ID, and blue LED ID. Okay, you are not allowed to create any other threads. Okay, and the terms here 0 plus, 1 plus, 2 plus refer to the time just after 0, 1, or 2 seconds. Okay, so let's see how we can go about it. Okay, so we can see that we have created the red, green, and blue. Okay, and the red is the highest priority. Okay, let me just check back. Green is medium, so this is the medium priority, and this is the lowest priority. Okay, so once I have created these threads with these various priorities and I start the OS, what will happen is I will run the red LED thread first, correct? And once I run this red LED thread, okay, what do I do? The first thing is I call OS thread flags wait, and I say I want to wait for the flags 0 and 1. So 3 here refers to flags, okay, in bit position 0 and 1. I want both of them to be 1. Okay, and of course, since I specified that I want both, because I say OS flags wait all, and I say wait forever, that means I'm going to be waiting. Okay, so I go to a block state. At this point in time, I'll go to a block state until the flags for bit 0 and bit 1 are both set. Okay, so that is the first thing that will happen. I will run LED red thread. Okay, I'll call OS thread flags wait, and since nobody has set any of the flags yet, I'll go to a block state. And once I go to a block state over here, the scheduler will come in and select the next in line based on priority. Okay, so I'll jump to the LED green thread over here. So when I come here, what do? I will switch on the green LED for 1 second. So that is the one of the objectives, correct? At time 0 plus, the green LED will be on for 1 second. Okay, once I do that, okay, I set the flag for the blue LED ID. Okay, so this refers to the LED blue thread. So I set the flag over here. So over here, what I do is for bit 0, I set the flag. Okay, for bit 0, and then I call OS delay. So when I call OS delay, I will go to a block state. Correct? I'll go to a block state. So when I go to a block state, what will happen? It will then select the next in line, okay, in the queue. So red is already blocked, okay, waiting for the flags for its own thread to be set. Okay, and since this green thread goes to a block state, I will then be able to switch over to the blue thread. So for the blue thread, what happens? The first thing I call is OS thread flags wait. I want to wait for the bit 0, okay, to be set. Okay, and what happens here is the flag has already been set over here, correct? So since the flags has already been set over here, okay, I will not have to wait at all. I will immediately be able to proceed to the next line, which is to switch on the blue LED. Okay, so that is the second objective. So this is the first 1 second, okay, where it is on. Okay, and after that, this is the second 1 second where the green is on, at the same time the blue is also on. So this is the time t equals to 1 plus. Okay, so this is 0 to 1, and this is 1 to 2. Okay, then after that, what happens? Okay, after this period of time, so I'm in block state for 1 second here and block state for 1 second here, and since the green thread is the first one to call the OS delay, it will come out of the delay first and it will off. Okay, it will off the green LED and it will set the bit 0 flag. So this one will actually set the bit 0's flag for the red LED, correct? And then I call delay. So I go to our block state, and subsequently what happens, very soon after that I'll come out of this delay, and then I will off the blue LED as well, and then I will set the bit 1. Okay, so this 2 refers to 1 0, correct? So this is bit 1 of the red LED. So when this occurs, what happens? This condition has now been fulfilled. So the moment this condition is fulfilled, I'll be able to come out of the block state to the ready state and then eventually run. Okay, and once I start running, I will be able to switch on the red LED. Okay, so when this happens, okay, this is basically the time instance from 2 to 3 seconds. Correct? This code over here. And once that is done, what happens? I go to the off state. Okay, I go to the off state, and then I off the LEDs, and then I look back over here. Okay, and what you see is the whole process will keep repeating itself again and again, okay, indefinitely. Okay, so this example basically tells us how we can sort of synchronize the behavior of multiple tasks, okay, using threads, thread flags. So you can see that one thread could wait for one or a few other threads to have completed some activity before they sort of signal this particular thread, and then it can carry on doing other things. Okay, so it helps us to synchronize. Okay, so we also saw this similar approach using semaphores. Okay, and now we are using it using flags. Okay, and the advantage of the flags is you have this total 31 bits for each thread itself. Okay, so multiple threads could have reached different parts of the code before another thread actually starts to carry on from where it left off. Okay, so that is one of the advantages of using thread flags over here, and this example shows you that quite clearly. Okay, for question 3, we are going back to using mutex, okay, to achieve an objective first. So in this case, we have two tasks, T1 and T2, okay, that access a shared unsigned character variable count, which is initialized to 0. Okay, and both of them have equal priority. Okay, and the objective for task 1 is to keep on incrementing the variable of count by 1. Okay, and whenever the count holds a value greater than or equal to 10, task 2 will be is required to reset the variable back to 0. Okay, and we're only supposed to do this using mutexes, okay, without any OS delay call. Okay, so how do we go about doing this? Okay, so this is actually quite straightforward from what we have already studied from mutexes. Since count is a shared variable, whenever I need to access count, I need to do this. Okay, I need to acquire the mutex and release the mutex. Same thing, I'm using count over here, so I acquire and then I release. Okay, so in this code here, what you will see is task 1 will be running, okay, and it will be incrementing, and since both of them are equal priority, okay, every time slice they will sort of keep on doing a context switch, okay, across each other. Okay, and what will happen is whenever I do a context switch over the task 2 and I realize that this condition has been fulfilled, then I'll reset it back to 0, and task 1 again will start to count again from 0. Okay, so that is how you can sort of achieve this objective using mutexes. Okay, now we are given the same objective, okay, but only thing is that task 1 priority is greater than task 2 priority, and we have now fulfilled the same objective using only event flags. Okay, so how can you go about doing it? So this code gives us an idea. So task 1, okay, will keep incrementing, okay, and the moment it hits a value of 10, it will set an event flag, okay. Okay, so of course the main code is not shown here. If you look back at the lecture slides, you will see that event flags can be used across multiple tasks. Okay, for thread flags, every thread has its own unique thread flags. Okay, but for event flags, multiple threads can write, okay, or wait for the same set of event flags. Okay, so prior to using event flags, I must create it first. Okay, so I must call the OS events flags new. Okay. Okay, so I need to call that first in the main, okay, to create a new events flag. And once I create a new events flag, then over here, what I will do is I am setting the bit 0. So over here, what I'm doing is I'm setting the bit 0 to a 1. Okay. And then after that, what am I doing? The next line immediately is I want to wait for bit 1 to be set. So this is basically telling that I want to wait for bit 1 to be set. So when this bit is set, okay, then only I'll be able to carry on. Correct. So since I only set bit 0 and bit 1 is not set at the moment, when I execute this line, I will go to a block state. Okay, so task 1 is higher priority, correct? The task 2 is lower priority. So when the system first runs, I'll execute task 1, but once it goes to a block state, I'll be able to context switch over to task 2. So when task 2 starts to run, the first thing is it waits for the events flag bit 0 to be set. And since this has already been done here, I will not need to wait. Correct? I will not need to wait. I can straight away go and proceed to the next line, which is to reset the count back to 0. And then what I do, I set the bit 1, okay, of the events flag. So I'm going to do this. I'm going to set a 1. So the moment I see a 1 here, this condition that I've been waiting for has been fulfilled. Okay, so from block, I will now be able to transition to ready and I'll be able to run. Okay, why? Because this is higher priority. So immediately once this line is executed, I'll be able to do a context switch over back to here to get past this stage and repeat one more time over here. Okay, so every time, okay, I go to task 1, I keep incrementing my count value. Once I hit 10, I will set bit 0 and wait for bit 1. Okay, that will allow me to do a context switch over to task 2. Okay, and task 2 will run. Bit 0 has already been set, so I'll just carry on to reset the count value and set the bit 1, which task 1 is waiting for. Okay, so the moment I do this, I'll be able to go back, do a context switch back, okay, to here, and from there carry on with task 1. Okay, so event flags, as you can see, are also a very useful way of synchronizing, okay, the behavior between multiple tasks. Okay, you could have done the same thing using semaphores, you could have done the same thing using thread flags, okay, and now you see an example using event flags. Okay, so of course there are a lot of different ways of doing this kind of fulfilling this kind of objectives where you want to synchronize different tasks together. Okay. Okay, so of course this brings us to the end of the tutorial here, but in our lecture slides, okay, and in the lab, okay, we also discussed about the message queues. Okay, so the message queues are also a very interesting and very useful tool because they allow you to do two things at the same time, data transfer, okay, at the same time synchronize. Okay, so of course try to go through those that lab, okay, to understand how you can actually code event flags, thread flags, and message queues to fulfill different types of objectives. Okay, so with that, that wraps up this tutorial. So like I said, please try to do the lab exercise so that you have an idea how all of this actually works. Okay, on the on our Freedom board. All right, thank you.